Example 1 is a long, simply supported timber beam carries a concentrated load P at the mid-span, that is 19 kips. Then the cross-sectional dimensions have been shown here. Okay, at the section AA, right, we cut it from here. At section AA, determine the magnitude of shear stress in the beam at point H. At point H is here. Then determine the maximum shear stress at the section AA. Okay, as we just analyzed, well, here the maximum values will be, if this is a global centroid, maximum shear stress will be here. Okay. Then, as derived previously, we have an equation. We just use that equation to determine the local shear stress values and the maximum global values. The shear stress equals VQ over IT. Right. At the cross at the section AA, well, as we analyzed before, you have 3 constant values in this equation. Right. What are they? What are the constant parameters? V is constant, I is constant, and T is constant, right? So the only variable is Q. Okay, so let's determine this constant first. So first of all, what is the V? What is the shear force at section AA? Well, to do this, we need to do a free body diagram and then determine the reaction forces and draw the V diagram. Right? We just simplify that. Whereas we have a concentrated P here equals 19 kips. And you have reaction forces as shown here, AX, AY, and CY. But AX equals 0, obviously. Right? So you will have just AY and CY. So you can simply determine that this AY equals CY equals half P. Right? This is AY actually equals 9.5 kips, and CY equals 9.5 kips. Right. So based on this, you can draw the V diagram. Right, the V diagram will be 9.5 here, negative 9.5 here. Right, 9.5, negative 9.5. Then at the section AA here, so the V equals 9.5 kips. Right? So we have determined that V equals 9.5 kips, and we have other constant values like thickness T. In here, the thickness T just equals B, by equals 6 inch. And another constant value will be I, right? The moment of inertia is a constant through the entire cross section. So it's a rectangular shape. So what is the I for a rectangular shape? That is BH cube over 12. Right? So here the B is 6, H 15 cube over 12. So that is 1688 inch to the 4th. Okay. Then we can start to calculate, to analyze point H. Right? At point H here. Okay. You just cut it through this point and get an area. Get area above it. Then you get the local centroid, and here is your global centroid. Right, so to calculate QH, right, the QH equals AD. So we just need to find what is A, what is D. Right? Because according to the analysis here, the A will be 6 times 3. Right? So 6 here, 3 here. Right? And then what is the D? Right? D is just y bar minus y of this area. Right? The y bar from top to here, this is the y bar, right? The y bar will be 15/2, right? Minus the y will be from top to the local centroid, well, that is obviously 3/2. Right? So the result here, you get 108 cubic inch. Right, then the tau h, the shear stress at point H, can be calculated as VQ over IT. Right? The V will be 9.5 kips times 108 cubic inch over 1688 inch to the 4th by 6 inch. So you get 0.101 KSI or 101 PSI. Okay. So this is the shear stress at point H. Then what is the maximum shear stress? Right, as we just derived previously, the maximum shear stress will be here. Right? But we do not need to do the geometry analysis again, since we have got an equation to calculate the maximum Q. Right? The maximum Q equals BH squared over 8. Right? So based on this equation, you can calculate that the B is 6, H is 15 squared over 8. Get 168.8 cubic inch. Okay, then the tau max can be calculated since the VTI are all constant, so the Q max means tau max, right? So the VQ max over IT. It's 9.5 kips by 168.8 cubic inch over 1688 inch to the 4th times 6 inch. So you get 0.158 KSI or 158 PSI.